Hey AP Physics. Today we're going to look at the 2.04 practice problems. I asked you to complete number 9 and number 13. Let's start with number 9. In number 9, the problem reads that the best leaper in the animal kingdom is the puma, which can jump to a height of 3.7 meters when leaving the ground at an angle of 45 degrees. With what speed must the animal leave the ground to reach that height? So let's start by drawing a picture, and I am by no means an artist, so please don't judge my abilities to draw a puma. Give me 1 second while I switch my pen. Okay. So here's our very terrible drawing of a puma. There's its ear and its eye and its mouth, body, legs, whatever. Here's a puma. So it is leaping at an angle, and it is making an angle of 45 degrees, okay? And we know that it's going to follow a path that looks like this, just like we saw in our pivot video. And I'm going to say that this is the ground here. And so we can label a few things. First thing we know is that our vertical acceleration is negative 10 meters per second squared. We know it's negative 9.8, which is the more average acceleration due to gravity, but we're going to round to 10 for the ease of calculations. We know that at its max height, it says that it can jump to 3.7 meters. So we know that the max height is equal to 3.7 meters. We don't know where it's going to end, but we do know that we can call its initial position 0 meters. And because we're assuming it's on the ground, we can assume its initial vertical position is also 0 meters. Notice here I'm using a y to dictate that this is the vertical acceleration. But like we talked about in class today, its horizontal acceleration is going to stay 0 meters per second squared. Okay. The problem doesn't give us anything about time, so we don't know anything about how long it takes for it to reach its max height or for it to get back to the ground. So I'm going to go ahead and start to fill out my lists here. So I'm going to start with the vertical section. We know that its initial position is 0 meters. We know, we don't know the final vertical position, but we'll talk more about that in just a second. Its initial vertical velocity, we don't know. Its final vertical velocity, we don't know, but I did forget to mention that at its max height, its velocity is 0 meters per second in the vertical direction. And again, we need to think about the video where she threw the ball out in front of her. And if we looked at just the vertical component, it went up, stopped, and then came back down. So that tells us at the max height of the jump, the velocity is 0 meters per second. We know throughout the whole flight, the acceleration is negative 10 meters per second squared, and we don't know anything about the time. Now let's look at the horizontal components. The horizontal components are equally as sparse. It starts at a position of 0 meters. We don't know where it lands. We don't know its initial horizontal velocity. We don't know its final horizontal velocity, but what we do know is that because in the horizontal direction, the velocity is constant, we know that its final horizontal velocity, or really at any point, its horizontal velocity is going to be equal to whatever velocity it started with. That is one of the keys when we're talking about 2D motion, is that horizontal component does not have any acceleration, and so that velocity is always the same. We don't know anything about the time again, so we can leave that blank, okay? One thing that you're going to want to start doing, though, is you're going to want to draw a very simple triangle that represents the initial situation. So we've got a triangle here, and we're going to break it up into its horizontal and its vertical components. We're going to label the hypotenuse of our triangle what I'm calling big V. So this is the initial velocity. This is the velocity that we could actually measure. We're going to want to label the angle, which is 45 degrees. And we should also go ahead and remind ourselves that if we want to find the initial horizontal component of that velocity, it's simply equal to big velocity times cosine of theta. And if you don't remember why that is, check the notes. Its initial vertical velocity is equal to big V times sine of theta. Okay? So often these are going to be our most important relationships, okay? Because it tells us that if we know big V, we can solve for our components. And if we know one of our components, we can solve for big V, okay? If I divided both sides by V and divided both sides by V initial, actually, you know what? Ignore that. We'll come back to that towards the end of the video. So let's go ahead and start to think through which equation would be appropriate, okay? So we've got our big three, V equals VO plus AT, Y equals YO, or X equals XO, whichever form you want to use, plus VOYT plus 1/2 AYT squared. And, we have V squared equals VO squared plus 2A delta X or Y, your choice. Okay. Doesn't matter. The same equations apply in both directions, like we've constantly seen. Just depends on if we're talking about horizontal or vertical. Okay. And what this problem is asking for is with what speed must the animal leave the ground to reach that height? And so it is asking us to solve for big V. Whenever you have an object that's moving at an angle and it's talking about the speed, it's talking about that big V, unless it's very specifically says the horizontal component of its velocity is whatever, then that would be Vxo. Or if it says the initial vertical component of the velocity is whatever, that would be Vyo. Okay, so you just need to be really careful about what it's talking about there. Okay, so it doesn't look like we have a lot of information, but we have more than you might think. If we want to know the velocity to reach its maximum height, we can start to use those numbers to understand a few things. So I'm going to actually say that for my vertical component, I know that when it's at a height of 3.7 meters, it has a vertical velocity of 0 meters per second. This does not give me any information about the horizontal. It only tells me about the vertical motion variables. Okay, and so with that information, I now know a change in position. I know the initial and the final. I know the final velocity, and I know the acceleration. So if I want to find the initial vertical velocity, I can use equation 3. And so equation 3 is Vy squared equals Vo squared plus 2A delta Y. And I can plug in 0 for my final, because at the very top of its height, its velocity is 0. I don't know my initial velocity, but that's my goal. That's what I want to solve for, and you'll see why that's important in a second. My acceleration is -10 due to gravity, and my change in position is 3.7 minus 0. Now, if I plug this all into my calculator and apply my algebra, I get that my initial vertical velocity is equal to 8.6 meters per second. Okay. And so one of the things that may be helpful here is to actually label not just VO, but VOY to let you know that this is the initial vertical velocity, and alternatively VOX, which lets you know that this is the initial horizontal velocity. The thing is, it turns out I don't need any of my horizontal information. And the reason for that is once you have one of your components, whether it's X or Y, you can use our relationships in our triangle to solve for the hypotenuse, or vice versa. So if we look at our VOY, our initial vertical equation, that is VOY or VYO, it doesn't matter what order, equals V times sine of theta. Now, theta is just the angle that it's being launched at. Big V is that hypotenuse velocity, the actual velocity. and VOY is the initial vertical velocity. So our initial vertical velocity is 8.6. Our big V is what we're solving for, and our angle is just 45. Now, something that you may, or that you're going to want to catch on to really quickly is that sine 45 is just a number that you can find using your calculator. So if we take a look at Desmos, we can prove this pretty easily. That sine 45 just gives us a number, which is 0.707, blah, 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 blah. Okay. So you could approach this one of two ways. Okay. First thing you could do is punch that into your equations. You get 8.6 equals V times 0.7071. I'll go ahead and round that. And then to solve for V, we're just going to divide both sides. 7071, and that gives us an answer of 0.6 divided by 0.7071. That gives us that big V is about 12.16 meters per second. Okay. Now, for your own algebraic knowledge, you don't have to convert it to a number in order to divide. I could also approach this problem by dividing both sides of sine 45. So I would get 8.6 over sine 45 equals V. I like this more because this means I only have to punch it into my calculator once. I don't have to do it 2 times. So I can do sine 45. And if we look at that, it gives me the exact same number. V equals 12.16 meters per second. And that would be our final answer. So that's a helpful tip to know. If you notice, if I go about route number 1, I have to punch sine 45 into my calculator, and then I have to punch 8.6 divided by 0.7071 into my calculator. But if I take approach number 2, I just have to do 8.6 divided by sine 45, and I get the exact same answer. Okay. Notice this first one is off a couple decimal places later because I had to round sine 45. And so doing it the second way is both easier because it requires you to go to your calculator less, and it gives you a more precise answer. So I recommend taking number 2. Okay, so that one is fairly simple when we look at it that way. Now let's take a look at 13. So 13 says that a brick is thrown upward from the top of a building at an angle of 25 degrees to the horizontal and with an initial speed of 15 meters per second. If the brick is in flight for 3 seconds, how tall is the building? So let's go ahead and draw out our building. We've got a person standing up here, and for some reason they are hucking a brick into space. Okay, and that brick is going to go flying. And if we think about it, it's going to go flying up and then back down until it hits the ground. Okay, and this is just one of those things that you'll pick up on slowly over time as you do more and more practice problems. Okay, so again, I'm going to draw my triangle to help me better understand this problem. And what it tells me is that we're hucking the brick at 15 meters per second. Because the problem doesn't explicitly say horizontal component of speed or vertical component of speed, it just says an initial speed. This is the number for big V. Okay. If we want to find the initial horizontal component of our speed, we do big V times cosine of theta. And if we want to find the vertical component, we do big V times sine of theta. Well, we also know theta because it says 25 degrees to the horizontal. And that's just a fancy way of saying if you have a horizontal line, you're measuring 25 degrees up from that, which is exactly what this triangle is. Okay. So this gives me this triangle here. And if you already start a problem with big V and your angle, I highly recommend just really quickly calculating your initial horizontal and your initial vertical. It'll just help you with your setup a little bit later. So I'm going to go ahead and enter these into my calculator now. Big V is 15 times cosine of 25, and that gives me 13.6 for my initial horizontal velocity. And then I'm going to do 15 times sine of 25, and that gives me my initial vertical velocity. Okay, and so if we think about this in terms of the real world, 25 degrees is, barely like this. So that means most of my speed is going in the horizontal direction and very little of it is going in the vertical direction, which is why those numbers are so different. Okay. Now let's go back to our diagram. Okay. What the diagram tells us is that the brick is in flight for 3 seconds. So we got to kind of think through that. That means that the total flight, this entire path, only takes a total of 3 seconds. So I'm going to label that T. Let's call this T equals 3 seconds. Okay. Now this is where we're going to add a few other things. Okay. So the brick is going to complete a full flight path. So it's going to go up and then back to where it started before it starts to go down the rest of the building. Okay. And this will allow us to highlight some other interesting points. There's the top of the flight path. That's the max height. And I'm going to say it reaches max height at a time of T1. And you'll see why I do this in a little bit. And we know that the vertical velocity at the max height is always equal to 0 meters per second. Okay. Another important thing to note, okay, is that if the brick is going up with a vertical velocity at the beginning equal to 6.3 meters per second, that's what we calculated. So VOY equals 6.3 meters per second. When it completes the whole flight path and it gets back to the same level that it started at, it will have that exact same velocity in the negative direction. Okay, so instead of being positive 6.3, it's going to have a velocity here of negative 6.3 meters per second. And if you think about a velocity time graph, that makes sense. It starts out at some positive point up here. Then it's going to slow down due to the acceleration due to gravity. It'll cross the 0 or the x-axis when it's at the max height, when it stops going up, and then it's going to change directions and start speeding up the other way. Well, because the amount of time it took for it to stop matches the amount of time it takes for it to get back to the same height that it started at, those two velocities are going to be equal, but they're pointing in different ways. Okay, and so I'm going to say that it does this at a time of T2 because that's another interesting time in the flight path. So T1 is the max height, and we know that its vertical velocity is 0. T2 is when it's at the same height as it started, but obviously further down, and that's a Vy of negative 6.3 meters per second. And then past that, there's not a whole lot else that we can label right now. We can go ahead and label our horizontal component of velocity, which is Vox, and we calculated that to be 13.6 meters per second. Okay. So with that in mind, let's go ahead and start to list out our variables, at least to start with. So in our vertical direction, we start with an initial position of we don't know, okay? And we're going to say that y0 is right here, okay? And we're still going to call the ground 0 meters. All right, so we don't know our initial position. That's our initial vertical position, and that's our ultimate goal for this problem. Okay, we don't know the final position because there's a few different places that are interesting. We do know the initial vertical velocity. That's 6.3 meters per second. We know the final we know the final velocity at the max height, and we know the velocity when it's at the same height further down over here at T2, but we don't know what the final velocity is. We do know that the acceleration stays the same throughout, and that's a result of the acceleration due to gravity, and the problem doesn't tell us anything about time. In the case of the horizontal, we can call our starting position 0 because we almost always can. We don't know how far it lands from the building. We do know our initial horizontal velocity, though, and that is what we calculated from our triangle. So that's 13.6 meters per second. We don't know, or we do know that our any other horizontal velocity is going to be equal to our initial. That's the rule when things fly through the sky. And because those are the same, the acceleration is 0 meters per second squared, and the time is an unknown as well. So ultimately, what I really want to be able to measure is what's the distance between where the brick started and the ground, okay? And so one of the ways that I can do this is I need to be able to measure this, this distance here, okay? And so if I can figure out how long it was falling between T2 and T3, I can calculate that height. So let me show you how I go about this. The first thing that I know is that at the maximum height, which we're calling T1, we know that the velocity in the vertical direction is 0 meters per second. Now, this becomes relatively handy because what I can now do is I can set up the equation v equals VOY plus AT, and I can solve for how many seconds it took for the brick to reach its maximum height. Its final velocity was 0 at this point. Its initial velocity was 6.3. Sorry, I keep forgetting to put my y's on things. Its acceleration was -10, and we're ultimately going to solve for the time. So after a little bit of algebra, I get a time equal to about 6.3 seconds. Okay. Now, at T2, it has returned to the same point. Okay, so we're now back at the same point here. And just like we talked about with pure vertical motion, the time it takes an object to get to the top is half the amount of time it takes for it to get back to the bottom. Okay, so to figure out what time it is at T2, we know that the time at T2 is just equal to twice that of time 1. Okay, so T2, the amount of time that it takes for the brick to get all the way over here, is just twice the amount of time it took for it to get to the top. So it took it 0.63 seconds to get from here to here. And so it's going to take it another 0.63 seconds to get from here to here, or in total, we can plug that in, which works out to be 1.26 seconds. Okay, so now we know that the brick is here at 1.26 seconds. So it took 1.26 seconds for the brick to go up and then come back to the same height that it started. And we're going to call this basically the top of the building. So that means I know it fell from the top of the building to the ground between 1.26 seconds and 3 seconds. So let's figure out how long it fell. Okay, so the time that it fell was the final time minus how much time it was already in flight, and that's equal to 1.74 seconds. Okay, so all I did there is I said, I know in total it took 3 seconds. Let me subtract how much time it spent just going up and coming back to the same height. And then the time that I'm left with is basically how long it took it to fall this distance. So knowing that amount of time, I can actually apply kinematics equation number 3 to figure out the height of the building. Okay. So like I said, we're going to call the ground, this is the final place. So what we're looking at is the brick is right here. So we're going to treat this point as our new initial, because this is the start of our measurement. And our ground is down here. So we're looking at when it lands on the ground, so when its final position is 0, we want to know how high up it was, that initial position at T2. Well, we mentioned at the beginning of our drawing that the initial vertical velocity, or the vertical velocity right at this point, is the exact same as when it started, just pointing in the opposite way. So we do know VOY is negative 6.3. Okay. Now the time it took to fall was 1.74 seconds. Our acceleration is still negative 10. We're going to plug in that 1.74 again. And if you look at this, this is all numbers with one letter. And if you solve this, you get that the initial position was 26.2 meters. And so what this number is telling us was that the block, or the brick, was at a height of 26.2 meters when it was right here. That corresponds to what we are calling the height of our building. And so that is how you solve problem 13. If you looked at both of these and you were like, I have no idea how he did that, the only way to get good at these problems is to keep solving them. If you can solve really only 5 or 6 of these, okay, which may take a long time for the first 2 or 3, but as you get to problem 4, you get to problem 5, and even if you do a 6th problem, you'll start to see that there are a lot of patterns on how to approach these problems. It's all about being able to identify those special points, such as at the max height, the velocity is 0, that whenever an object comes back to where it started, its vertical velocity is the same but opposite. It's recognizing that the horizontal velocity is the same throughout. And really, it's about mastering this component triangle right here. Once you can do all of that confidently, these problems will be a breeze, and they will set you up for success for so many other problems. So hopefully this was helpful. If you have any questions, message me, and I will see you all tomorrow.